All right, let's do another CSES math problem. Just like yesterday, this is actually also a graph matrix exponentiation problem. So let's take a look. This is graph paths 2. So we have a directed weighted graph having n nodes and m edges, right? So every edge has some kind of cost or length or weight. And directed just means it's not symmetric, so you can have an edge from A to B, but not from B to A. And we want to calculate the minimum path length from 1 to n of the paths with k edges, right? So among all the ways to get from node 1 to n, along with k edges, what is the minimum cost, right? Where every edge has a cost. So let's just think about sort of how you would do that, and then we'll see how to do it with matrices. Okay, so let P be the adjacency matrix. Pij equals min cost edge from I to j. Right, so we're allowing multiple edges, in which case we just take the minimum. So note that Pij is the min cost path. Min cost path from I to j with one edge, right? So that actually sort of solves the problem for k equals 1. So maybe you might hope that the same thing that was true last time would be true, and p squared ij would be the min cost path, 2 edges. That's not right. So let's see why. So p squared ij, by the definition of matrix multiplication, is the sum over the middle edges of pik times p, or the middle vertex, and pik times pkj. And that's just like not the right formula to find the min cost path from I to j. Right? We're taking a sum and we're multiplying. This actually would be the right formula if we were taking a min and we were adding. Right, so that's what Pij. But actually, it should be the min over k of Pik plus Pkj. Right, the length of the path through k is just the sum. Right, that's like how we're computing the the length of the path is just the sum of the weights of the edges. So the length of a concatenation of paths is just the sum of the lengths of the two paths. Right, so the length of the path from I to j through k is just from I to k plus k to j. And we want the minimum cost path, so we should just take the minimum over all of those possible paths. Right, so brute force over the middle vertex and take the minimum. And this actually would be a correct formula. But matrix multiplication does this, which is wrong. But we can actually just change our matrix multiplication formula to, instead of doing a dot product, being like a min of the sum. And then everything will actually work out, which is pretty cool. So it's the same argument again. Right, so this is not really multiplication. Say some question mark operator. And so this, this was just for length 1, but it actually works for any two lengths, sort of similar to the previous video. Right, and basically the argument that we were giving here is the same argument. To figure out the min length path, the min path of length a plus b from I to j, you can brute force over where you are after the first a edges, and then the cost of that path is the min cost to get there in a edges, and the min cost to get to the end from there in b edges. and you want to take the minimum over all of those. So if you just do sort of the normal matrix exponentiation, but with this weird operator instead of multiplication, everything actually works out. So let's do that. So these are floats. We will need to make a couple adjustments. Right, so before, if there is no edge in ij, not 0, but we're going to do infinity, right? Because infinity is going to work better with mins. Because if you put in 0, then like this would come out to be 0, even if there was no path. But we want it to come out. Yeah, if we make it infinity, that's yeah, that just plays better with min. It comes out to infinity if there's no path, instead of like a no path, because we want a no path to be worse than a path, right? But if we set no path to 0, then no path is going to be better than a path. And what can we use for infinity? So we want something that's bigger than going to be than any possible path. What's the longest path we could have? Well, it would be 10 to the 9 edges, each of cost 10 to the 9. So that's 10 to the 18. So we'll just make infinity a little bit bigger than that. We don't have too much room to work with, right? The maximum possible 64-bit integer is something like 9 times 10 to the 18. But 5 times 10 to the 18 should be fine. And notice there's no mod in this problem because we can actually compute the path length. Right, the number of paths is like enormous exponential, but the minimum path length is bounded by 10 to the 18, right? It's k edges of length c. Okay, so we had n and k. We read those in, and now we can read in the actual edges, which I assume is going to be start, end, and cost. Sure. PAB equals min PAB C, and A and B are one indexed. And again, we're just going to take into account that there could be multiple edges from A to B. I'm not sure if there are in their import or not. They're not very clear about it. They should be, but it's fine. We can just deal with it. Right. So this is another good reason to start infinity, is that any real edge is going to override infinity under the min. So like infinity is like identity for min. It's pretty helpful. Okay. I set vector vector, we're going to declare a type def for that. K equals matpow pk. I'm still going to call it matpow, even though it's like this weird operation. And we said we wanted pk 0 to n minus 1. Right, because we want from 1 to n. Yep. Except what if there are no paths? So in that case, we should get infinity. So just mark that down. So if there are no paths, we're going to get that pk of 0 to n minus 1 is infinity. And the problem tells us that we should write -1 in that case. So we actually need to check for that. It's a special case. And if there is a path, then we just write down the value of that path. LL equals n64t. Mat is a vector of LL. So this is like a weird matrix multiplication, right? It's not normal matrix multiplication. It's going to be this operation. But actually it looks very similar. But because we're doing mins, we want to start everything in infinity. Cij is is the min of Cij and Aik plus Bkj. Right, so normally we would add and multiply, but we said that here we want to do min instead of sum and plus instead of times. And so importantly, we need that 2 times infinity does not overflow, which is why I changed it from 5e18 to 2e18. I think 5e18 might actually overflow. 2e18, so the maximum length path is 1e18, so 2e18 is bigger than that, and the 2 times that plus that is not going to overflow. So that should be okay, but it's a little bit, you have to be a little bit careful. Mat tau is actually exactly the same as normal, as if we were doing sort of normal power, because it's all wrapped up in the multiply function, the rootness. Mat mul, AA, right, this is the magic exponentiation by squaring trick. Not magic, but cool. Anyway, otherwise we just take off the power of A, and that should actually be it. Now I'll just declare info here, 2a18. $27. Okay. So let's try it. This might be too slow. Oh no, because there's no mod this time. Wait, previous video it was yeah, the mods were slow. Okay, so cool. So that worked. Yeah, so this is a nice example of like if you understand the technique, then you can modify it to solve a new problem. Right, so like if all you knew was that like matrix exponentiation on the adjacency matrix counts the number of paths, you might have thought about that and like, does this work for this case? Well, no, because the min length path is not really the same as the number of paths. But if you actually understand the innards of the technique, you can see that you can modify it. All right, and put in min instead of sum and plus instead of times. But the key idea that you're still brute forcing, right, that like dot product in matrix multiplication corresponds to brute forcing over the middle vertex, that actually, that idea carries over perfectly fine. So if you understand that idea, then you can see that you can actually modify this idea accordingly, and it actually solves the problem. So that's pretty cool, I think. And yeah, it's another application of matrix exponentiation. So hopefully you also thought that was cool, like I did. Yeah, that's the problem.